Hello, in this video we'll present the context-free languages and show how are they associated to context-free grammars. Recall that in the last chapter we discussed a lot about regular languages and showed that there are languages that are not regular, like for example L1 or L2 or L3 here. And we proved by using the pumping lemma that A to the n, B to the n, for example, is not regular. Let's see now if there are more sophisticated way to design this kind of languages. For this, let's dig into the context-free grammar concept. This is used in general to see if a text follows some rule. For example, for this Python code, if we want to prove that this is a correct Python code, we need to see the rules associated with the Python language, which we will use to prove that these sentences are correct compared to the syntax of the Python language, for example. It's the same for the English language. If we have an English sentence like this one, it's a beautiful day. In general, an English sentence is composed of a subject and a predicate, and we have the rules to use if we want to see if this sentence is correct according to the English language. Same for the French language, for example. If this sentence, j'aime la programmation, is correct, it should be correct compared to the syntax of the French language. Okay, so this syntax is in general defined by a context-free grammar. To simplify it more, let's take this grammar for binary numbers. It's in fact a list of rules here, okay, or a rule that defines the binary number. Let's say, for example, that a binary number is represented by the letter B here, and we will say that B can be substituted to 0 followed by another binary number B, or else any number that is binary can be substituted by a sequence of 1 followed by B. Also, B may be substituted to epsilon or the empty string. Okay, this is a grammar for binary numbers. We'll show now how it works. We will apply derivation to check if some string is accepted by this grammar. Let's take, for example, the string 0110. Here we can apply the rules. These rules will be applied to show that this string is correct. It's a binary number. How to apply the rules? It's simply a fact of substitution. Okay, we substitute the first symbol, which is here B, by 0B. We have applied the first rule here, B produce 0B. After that, we will have a string here of two symbols, 0 and B. We will try again to substitute the symbol B, which appears in the second place here, which appears after 0. We'll say that this B will be changed by 1B according to this rule. Again, we have a B here that will be changed by 1B according to the same rule. And for the last B here, it will be changed by 0B. We'll apply the first rule here again, and we will see that we have now all the 4 characters here, or the 4 digits, have appeared here, 0, 1, 1, 0. So the last b here will be changed by epsilon. So we will result in the string 0, 1, 1, 0. So this work here shows a derivation of the string 0, 1, 1, 0. A derivation is a sequence of substitutions to obtain the desired string. We can also look for some derivation in order to obtain some random string. Okay, we say that we can generate strings. For example, here we applied a set of random substitution in order to obtain the string 0, 0, 1, 1, 0. We say that we generated this string, and we can generate many strings according to this grammar, since it's recursive. Each b produces another b, and the other b may produce another b, and so on until the last b will be substituted by epsilon to obtain the string. Okay, and we can say that the set of all strings that can be generated by derivations compose the language of this grammar. Okay, so here the definition of a context-free grammar. We can say that a context-free grammar, simply noted here CFG, is a four-tuple V sigma PS, where V is a finite set of symbols, known also as non-terminal symbols, or also known as variables. Okay, and the second term of this list is sigma. Sigma is a finite set of symbols. It defines the terminal symbols, and the sets V and sigma are disjoint. For P is the set of production rules of the form A arrow W, where A is a variable, it's in V, and W is a list of terminal and non-terminal symbols. So after the arrow here, we put any sequence of terminals and non-terminals, any sequence of symbols of V and also sigma. The last component here is the start symbol. S is one symbol of the variables, which is chosen to be the start symbol. According to this definition, for the previous grammar of the binary numbers, the set of variables here is B. The set of symbols of the alphabet is 0 and 1. Here we have 0 and 1. And the set of productions is the three productions B arrow 0B, B arrow 1B, and B arrow epsilon. The start symbol here is B. We have only one variable, and it's also the start symbol. Let's now apply what we have learned to design a context-free grammar for the language L1. Language L1, recall that it's in the first slides, and it's the language of the strings composed of a list of A followed by a list of B, where the number of A equals the number of B. Let, for example, the following string A to the 7, B to the 7, or 7 A's followed by 7 B's. For this, let's try to find the list of rules that can be used to derive this string, or that can be used to say that this string is correct according to the language definition. Okay, here we have to find a way to tell that this string is composed of a list of A followed by a list of B, and the numbers of A and B are the same. Let's say, for example, that we can suggest to say that this A corresponds to the last B, and the string in the middle will be another string that we can work in with the same manner we worked with the initial string S. Okay, if this is the string S composed of 7A followed by 7B, we will decompose in 3 parts: A and another string and B. In other words, let's say that this S will be A concatenated to another string S1 concatenated to the letter B. And for S1, we will say that it's the letter A followed by another string followed by this letter B. The string in the middle will be S2, and for S2 also we'll decompose in 3 parts: A, another string, and B. And we'll do this many times until we find just A with a B, and the string in the middle here will be epsilon. In this case, we will stop and say that the initial string A to the 7, B to the 7 is correct, is accepted by this language. Now we have the idea, we have just to write the rules by the same way we saw previously, and we can write, for example, that a string is divided into 3 substrings. The first one is A, the second one is S, and the third one is B. And we will see here that this definition is recursive, and we will stop the recursion here by S substituted to epsilon. Okay, this is the same as writing S derives A, S, B, or epsilon. We can use this vertical bar here to say that this is another production for the variable S. The formal definition for this grammar is the 4 components V, sigma, P, S, such that V is the set composed of only the non-terminal S. Sigma is composed of the 2 symbols A and B. P, the set of productions, is composed of S arrow A, S, B, and S arrow epsilon, and the start is the variable S. After designing this grammar, we may check if the string AAA triple B is accepted. For this, we can apply the first substitution: S derives A, S, B. So this A appeared and also this B appeared. For the S here in the middle, it should lead to AA, double B. So we will apply again the rule S derives A, S, B, while we write also this A and this B. So we'll obtain the string A, S, double B, and the S in the middle again will be substituted by A, S, B a third time. And since we have 3A in the beginning, we can say that this S will be changed by epsilon, and we obtain the string AAA triple B. We can say also that S arrow star AAA BBB, which means that we have obtained a number of substitutions that lead from S to this string, and this is proof that this string AAA is accepted by this language, since it can be generated by the grammar corresponding to the language L1. And here we say that the language of the grammar is composed of all the strings W in sigma star, such that W can be derived from S. Now, for a string to be derived from the start symbol S, we can also try to draw a parse tree. Okay, a parse tree is another method to make sure that a string is accepted by the language. For the same example, AAA BBB, we can draw the following parse tree. We can say that first we will apply S derives A S B. Second, for this S, we will say that also it will be substituted by A S B. Also for this S, it will be substituted by A S B. And the last S will be substituted by epsilon. So this tree is composed of nodes and leaves. For the leaves, we should find the string A, B, B, B. Here we have A, then B, B, B from left to the right. And the internal nodes correspond to the variables that are substituted each time to produce another set of symbols. Now try to write a context-free grammar for the language L2, which is the set of all the strings that may be written as WW reverse, with W in AB star, which means that it will accept the strings of the form A, B, B, A, which is composed of two parts. The first one is AB and the second one is BA, the first part reversed. Okay, another example is BBA and the second part will be A, BB, for example. Okay, try to find this grammar and write it in the comments. Also, try as an exercise to write a grammar for L3, which will accept all palindromes over AB. For this language, L2, it's in fact all palindromes with even number of symbols. Okay, and here another variant of the palindromes which accept even or odd number of symbols. Okay, try to find these two grammars for L2 and L3 and write them in the comments below.